So our last unit in calculus is integration. And I don't know if you remember in some of our first unit and our second unit that every once in a while I had a question that said work backwards. And you just had to undo what the derivative was, like the derivative was done already and you had to undo it. Well, in a very simplistic way, that's this unit. We're done. We're finished this unit. Test is on Monday. No. But that's the basic idea. The basic idea is it's the opposite of differentiation. However, when you get into more details and stuff, there is obviously more to it than just that. Now, integration actually was done a lot earlier than differentiation. So, and the reason for that is one of the main applications of integration is finding an area under a curve. So here we have, let's say, a parabola, and let's say the x-axis and y-axis is there, and you're like, I wonder what that area is. Well, the first people would have said, I could find that area by finding the area of this rectangle because I know that formula. And if I make this a triangle, it's pretty close. So that's not bad. And, you know, mathematicians are not usually very happy with pretty close, right? So if someone says, I can get pretty close, someone else says, I can get closer. And then the war is on to find how to do it exactly. And so the idea became saying, well, if we know how to find areas of rectangles, take away my first drawings, what happens if I made little rectangles all along like this? How close would my estimate be? And so someone said, ooh, my estimate's better than your estimate, right? Because I made little rectangles. And the next guy says, well, I'm going to make littler rectangles. And then I'm going to make littler rectangles than your little rectangles, and so on and so forth. And we have this idea of getting rectangles infinitesimally small. And if you kept getting smaller and smaller, eventually you would get the area exactly. And that idea is really related to calculus, because same thing with your tangent and your secant line, as you brought your slopes closer and closer and closer and took that limit, that became your derivative. So this was the idea. Interestingly, later we found out that finding the integral, or doing this kind of idea, was exactly the opposite of finding the derivative. So anti-differentiation, if we're putting some highlighting things in here, that's the reverse process of differentiation. So if you had f prime of x equals 2x, what is the original function? So what would the original function have been if your derivative is 2x? X squared. Now, is that the only answer? No. It could have been, and this is where, like, if it just asked for 1, you could add your favorite number here. If your favorite number is 73 and you haven't used it for a while, you could have written x squared plus 73. And one of the things that we're going to do here is we're going to say plus c, because it could have been any number. Even though you really want to put 73 down, that's okay. But it could have been any number there, then that would be the antiderivative, because there's an infinite amount of possibilities. Some notation. So what we write when we want to find the integral, we've got our integral sign. It looks like a big stretched out S. The inside is called the integrand. And notation-wise, so if the question that we had before, what we figured out was the integral of 2x, saying can you work backwards from 2x, and this part, the dx, is just telling you which variable are you supposed to work back from. So if you had 2x and you were integrating with respect to x, then you would be going back with x. Sometimes that notation, sometimes we would have a different variable there. So x is the variable of integration, and we can tell that by the dx. And the c afterwards is just your constant of integration, because after you do the integral, there could have been any constant there in the derivative to begin with. So here's just some language stuff, right? In one direction, this isn't in your books, but just as a visual, in one direction you're doing the derivative, in the other direction you're doing the antiderivative. Sort of talking, if you started with a function here and you went this way by taking the derivative, you would say this is your derivative. If you started with the function and worked backwards, then whatever function you would get, you would call your antiderivative. So we've already done this, but we're going to develop the process more systematically than we did before. Like with the 2x, you could just see that it was x squared. But if I gave you something like 7x cubed and you had to work your way backwards, what are some of the patterns that we've noticed over time? Well, when you take the derivative, you always subtracted 1 from the exponent. So when I'm going backwards, the antiderivative, I would have to add 1 to the exponent. And I picked 7 out in front purposefully because it doesn't work out nicely. Because now I would think, okay, I just have to put 4 times what is 7? And it's not a nice number. It's not an easy number to put down. But if you think about what happens when that number came out in front, it multiplied, right? Whatever is here, and by the way, it's going to be 7 over 4, because if I multiply that by 4, I'm going to get 7. Whatever number's in front, we usually multiply by, so if we're working backwards, we're going to have to divide. So here's our process when we found the derivative, right? We multiplied by the function by the exponent. That 5 came out in front, and then we subtracted 1 from the exponent. So now working backwards, and here are some from the unit 1 that you did. What we do is we add 1 to the exponent, and then whatever number was in front, we divide by that new exponent. Here, again, we would add 1 to the exponent, and these ones you could probably just see because the numbers work out nicely. But if I took 12 and divided it by 3, I would get 4. Now, the majority of the time, you don't have nice numbers to work with. And because of that, we develop this process where we add 1 to the exponent, and then we divide our new function by our new exponent, and then add the constant c. So let's take this example here, 12x squared, and let's say the derivative was 12x squared. Using this new process, it says add 1 to the exponent, x cubed. The 12 stayed out in front, and now divide the function by the new exponent, divide by 3. Now you might say at this point, oh, Mr. JR, I could see that it was 4 right away. Why would I do that extra step? Because now, and then we'll add c to it. Why would I do that extra step of dividing? Well, it's exactly in the situation where you have something like this. Not a pretty number. But if this was the derivative, and I was finding the original equation, well, I would add 1 to the exponent and divide by my new exponent. And now I have fractions over fractions, so I can simplify this and I can tell you right now that in this situation, when you saw this, and here's the answer of working backwards, is it really obvious that the 2/3 should change into a 1/12? No. It's not really obvious that that 2/3 should change into a 1/12. So this process of dividing by the new exponent is going to be really helpful, even though some of our earlier examples were ones that you could just see. Oh, speaking of seeing it, I'll add C to both of those. So we can write this out in general. What does it look like? If you have any function, x to the n, the opposite of your power rule, you add 1 to the exponent. You get x to the n plus 1, and whatever your new exponent is, you're going to divide by that. And then add your plus c. Why can't n equal -1? Because if you added 1 to the if you divided by your new exponent, you get 0. Whew. Just for fun. Let's put it as, it says x can't equal -1. I'm going to give you a challenge here. What's it equal to? I know, we get this later in our notes, but it's so fun to challenge you now. You know this one. Work backwards. Okay, you know this one. You're going to have to not think about your power rule. It is the natural log of x. What's the derivative of the natural log? 1 over x. So if you were integrating an x to the -1, which is a 1 over x, you would get the natural log. That one's really hidden. When you do derivatives, when you see natural log, you're like, yeah, that's a different one. I know how to do it. But when you're working with antiderivatives, when you see an x to the -1, your head will go power rule, power rule, power rule, and then you'll get stuck. So when n is -1, it doesn't work because that's when the natural log appears. Same thing if you have a value out in front, you still add 1 to the exponent and divide, just like we did with that 2/3. That 2/3 stayed out in front on that previous example that we did right here. 2/3 stayed out in front, we divided by 8, and then we just did arithmetic, how do you divide by fractions, to simplify that equation. The nice thing about integrals, if you're unsure if you did it right, you can always take the derivative of your answer to check. And if you take the derivative of your answer and it works out, you're like, yes, I did do it right. And if it doesn't work out, you can say, yes, I was unsure. Indefinite integral, so if I write notation of this in math symbols, this is what they're asking. What's it going to be equal to? Add 1 to the exponent and divide, plus c. Now, over time, I'm going to say, I'm going to accept if you just write plus c, you don't have to tell me every time that c, it can be any real number. But if you want to be really you know, if you add a variable like c, you should define it. So it is good practice to write that c belongs to the real numbers. Okay, a couple for you to try. Quick check. How did you do? Okay. Playing around with notation. Sometimes if the original function is f of x, when they do the antiderivative, they use a capital F. So f of x would equal, add 1 to the exponent, divide by your new exponent. Whew. That was disastrous. And I have to warn you, your brain is going to go through a little bit of a problematic stage. Because you've been doing the derivative for so long that you've been getting good at it. Then you're going to have to work backwards. And then sometimes in questions they're going to say, work forward, work backwards, work backwards, work forward, forward, backwards. And your brain is going to get them mixed up. It's already bad with negative numbers. Some of you had trouble subtracting 1 from negative numbers, and now you have to add 1 to negative numbers. So just take a deep breath. Don't go too fast, because you're going to find yourself making lots of little easy mistakes if you do. This one's missing a dx here. Sorry about that. First of all, I would change this to an x to a half, and then we add 1 to the exponent, divide by our new exponent, plus c. Dividing by a fraction is the same thing as multiplying by the reciprocal. Mm-hmm. Yeah, well, they don't like fractions within fractions. So in this case, you would have to simplify this. And again, look what happens if you take the derivative. If that 3 halves came out in front, you see the 3's would cancel. You'd be left with 20 over 2. 20 over 2 is 10. Perfect. My number in front is correct. So I can do a quick check to see if the number is right or not. Different notation, integral of y dx. Well, what's y equal to? Y is equal to x to the 3/7. So I can substitute that in, and I changed my radical to a fractional exponent. Add 1 to your exponent, divide by your exponent plus c. Multiply by the reciprocal. Do a quick check. Can you see that if I bring the 10/7 out in front, it'll cancel with the 7/10?